Hello everyone. Today we'll be discussing about the stack data structures and its basic operations, and let us also see how it is implemented using arrays and linked list. So I have shared my screen here. In general, what do you mean by stack? So stack is nothing but a pile of objects that are placed one over the other. So we can visualize the stack as the stack of books as vertical vector. Let us assume all these three sides are closed. So the basic principle what the stack follows is LIFO principle. LIFO is nothing but last in, first out. That means the last element that was added is the first one to be removed. So let's say this is the last book that was inserted on top of the stack. So this is the first book that customer will buy. We'll take it from the stack. So in the same way, in the context of computer science, stack is nothing but the data structure that stores element in the LIFO principle, using the LIFO principle. So let's say this is the top of the stack, and these are the elements that got added into the stack. So this is the basic stack structure. So the elements were stored into the stack in the LIFO principle, using the LIFO principle that is capable of few functions, few fundamental functions. So let me explain those fundamental functions. You can also call this a fundamental operations that we can perform on every stack. So those operations include push, pop, peek, is empty, and is full. So whenever we call a push operation on the stack, it will push the element on top of the stack. So here, let's say it is a stack and you want to insert an element, it will push on top of the stack. Let's say we need to push 5 into the stack. It will insert 5 on top of the stack. And in the same way, if you apply pop operation on the stack, it will remove top element from the stack. Here 5 is the top element and it will be removed. It will be removed. Pop. So basically, if we are inserting, it means we are pushing an element. And if we are removing an element, it is known as pop. In the same way, we have another operation called peek. So peek is nothing but it will just return the topmost element of the stack. So here the topmost element before popping is 5. So it will just return this topmost element. So there are few pointers and few other methods that can be implemented using stack that I will be sharing you moving forward. So these are the basic functions here: push, pop, peek, and there are the two operations that include is empty and is full. So these two are Boolean functions, Boolean operators, where it will says if the given stack is full or not, or if the given stack is empty or not. So this is the basic C++ program, how the stack is implemented. So we just created an object of stack type, stack class of integer type, and we're pushing few elements over here. So just like this, we are pushing 10, 20, 30, and 40, and then we are pushing the 50. So here 50 is the topmost element. So when we apply peek, it will just return the topmost element. So it will return 50. So after popping, it will just remove 50. So here in the peek, it will just return an element, return the topmost element. Whereas in case of pop, it just remove the topmost element, and then decrease the pointer to 40. So I will tell you more about the top pointer, how it is implemented during its implementation. So this is how it's worked. Let's say it is an empty stack. I'm not pushing one element, and then we're again pushing one more element, and then pushing one more element, and then popping the last element. So as I told, it will be implemented in using two ways, either using array or using a linked list. Okay, for now, let's see how we can implement using an array. So let us assume, for this example, let us assume an array called data. So the bottom of the stack will be the first element of an array, right? And the top of the stack will be length of the stack -1. So let me draw here. Let's say this is an empty stack. So we can visualize this empty stack as an empty array. So this will be the array. Let's say it is data. So array is named as data. So in the array implementation, the top we will be denoting a variable called top, and we will be initializing it as -1. So it has a -1. It is a 0th element, first element, and second element. So it is an array. So when the stack is empty, the top will be -1. And here we're pushing element called 1. So during push operation, it will check. We will be checking if the array is full or not. Let's say this is an array of size 3. We can accommodate only three elements into the array. We cannot accommodate fourth element into the array. So to calculate that, we will be just checking if the array is full or not. So it internally calls if it is full or not. So if it is full, if the array is full, we won't be able to insert an extra element into an array. Or else, what we can do, we can increase the top pointer by 1, so it will be 0. So the top will be 0 here. This is the top pointer. It will be directed to first element here, first index. So it is the 0th index. So -1 plus 1 will be 0. Top will be incremented, and then data will be pushed to the stack. So one is pushed here, one is pushed to the stack. In the same way, if you want to push number 2, it will again check for if the array is full or not. If it is full, it will throw an error, or else it will insert the element it will insert an element on top of the stack and then increment its top pointer. So here top pointer will be 2, top is equal to 1. So it will insert element at first index, and top will be 1, and top will be 1. Same way, if you want to insert 3, it will check if array is full or not, and then it will insert on top of the stack. So this is a stack of size 3, let's say. I mean array of size 3. It will be inserted on top of stack. So second is the topmost element in the previous iteration. So it will be added on next to 2. And the top will be incremented by 1. So top is 1 here, and then we're incrementing to +1. So top will be here 0. The second iteration it will be 1, and in the third iteration it will be 2. So that's how the push operation works in the arrays. That's how we can implement it using arrays. So basically during push operation, we will just check if the array is full or not. If it is full, we just throw an error, or else we can just insert an element. If it is less than if it is less than the size of the array. Since we have assumed the size is equal to 3 in this fixed array implementation, so let's suppose think of this case. Let's say if you want to insert into, so here the stack is full. So here the stack is full, but still you want to insert an element. So you want to push an element on top of the stack. So when we actually think of the actual use cases outside, we cannot implement it using a fixed size. So in Java, we use array list, but internally it follows array, where it will be all the elements will be copied, and then it will be formed as a new array list. So that's a different, but still it's the same concept. So we have a concept called dynamic arrays. Let me show it. Let me draw it on the next slide. Yeah. Let's say we have inserted 3 elements onto the stack. So 1, 2, 3, 4. Two, 3. So all the elements got inserted. So this will be the top. So 3 will be the top here. But we want to insert a new element. So that is 4. So in this case, what we do is we'll create a temporary array of size double of initial array. Let's say it is an data array is named as data. So we'll create a new array of size data into 2. So here the length is 3. So we'll create an array of size 6 where we copy all these elements 1, 2, 3, and then we can push the 4th element here. And then we can point temporary to data. So after copying the initial array, all the data values of initial array to a temporary array, and then we can again point the temporary variable to a previous array. So that's how the push operation works if it is an dynamic array implementation. So this is an algorithm. So as I told, if you want to push an element, it will check if the stack is full or not. If it is full, it will show an error, or else it will increase the top of stack by 1 and then insert a new element at the top position of the stack. And then it will return the top value. I will also be sharing the Java implementation of this once the theoretical part is done. So as like popping elements is nothing but just removing an element from the top pointer. So in this array, the top element is a 3. So when we apply pop operation on the stack, 3 will be removed. 3 will be removed. So in this case, the top pointer will be reduced to -1. So here top is 2 and it will reduce to 1 since it got deleted from the stack. So the new top will be 2. If we apply pop once again, the new top will be 0. It will be deleted from the stack. So it will be the top element. So while applying a pop operation, it will check if the array is empty or not. If it is empty, it will throw an error. If it is not empty, what does it do? It will just print the topmost element. So here data is an array name. It will print the topmost element. So topmost element is nothing but the where the top pointer is there. Here the top pointer is at 0th index, so it will be data at top. So it will remove the element that is at the first index of the array. So this will be removed. Okay. So when displaying elements from the stack, let's say top is equal to -1. Like before initialization, I told like top will be -1. So if it is full, we won't be pushing an element. If it is not pushed, if it is not full, we'll increment top to 1 in every iteration and then pushing an element. So here top will be 0 and element will be added, right? So if the top is -1, that means the array is empty. So we won't be, it means there is no element present in the array. So we won't be printing any elements. So if the top is more than -1, in the else case, what we can do is we can iterate over every index of the array 0, 1, 2 till the size of the array. So it's how it works. Zero, 1, 2. So this is the topmost element in the stack. So we will print 2 and then we will print 1 till we print 0. So 2, 1, 0. Is that all? First element, last element that got pushed to a stack is the first one to be removed. So the pop operation, it will remove the topmost element. So it is the topmost element here is 2. So it will just remove the second index, first and then 0th index. So that's how we can display elements on the stack. So before going through analysis, we'll just go through the code and then stack.java is the inbuilt Java class provided by Java. So it just extends vector class and implemented these operations: push, pop, peek, empty, and the search operations. So these all operations we have implemented using arrays and linked list. So I will be just showing here. So let's initialize the data array of type int. So let's name it as data, and let's keep the default size as 10. So if there is no size mentioned, if there is no size given by user, we'll just take the default size as 10. So we can call this as a constructor. So if no size is mentioned, it will just call the above constructor and will take the default size as 10. So this is a push operation here. It will, as I told, while pushing an element to the stack, it will just check if the array is full or not. If it is full, it will just return it will just show as an error, or else it will throw an error. So here we're printing the stack is full. If it is not full, we are incrementing the pointer to +1, like top pointer we are incrementing to +1, and then we are inserting the data that pointer. So we're incrementing the top pointer -1 to 0, and then we're inserting data of 0 at 0th index. And the pop operation, during the pop operation, we will be checking if the array is empty or not. If it is empty, we cannot pop any element from the stack, so we just throw that exception. And then if it is not empty, and let's consider this as the top of the element, the topmost element will be removed, and the pointer will be reduced by -1. So the top pointer will be here. This will be the top pointer. So this will be the topmost element. So that's what it says. The removed will be removed from the topmost element. Topmost element is nothing but the data where the pointer is, the topmost pointer is. And then we reduce the pointer to -1 to -1 in every iteration, and we'll just return the removed element. So how we check if the array is empty or not? So when it is empty, the top will be always be -1. So if it is an top is equal to -1, we can say the array is empty. How we can say the array is full? Let's say all these elements are got filled into the array, and how can say if it is full? If the pointer is at the, what is 3 here? Length of this array 4 -1. So if data of this length -1 is equal to top, we can say this array is full. So that's how we have implemented full, empty, peek, push, and pop operations using arrays. Oh yeah, let's look at that complex analysis for insertion and deletion using arrays. So during push, as I told, we will be checking the if the array is full or not. So we just check the topmost pointer, data's topmost pointer, and then if it is not full, we'll just remove the pointer to, we'll redirect the pointer to a correct location, like we are minimizing the pointer. So this, it will take a constant time. It will take a constant time. Same when we consider a pop operation, it will check the topmost element if it is not empty, and will just pop. So it won't be taking any extra time, just a constant time. So for one element, it will be 1, and for second element also, it will be 1 step. If we are removing second element, if we are removing third element, will be take just a constant time. So constant time, we can note it as an O of 1. So this is for fixed arrays. This implementation is for fixed arrays. Let's consider, as I told, if the array is full, I mean, if the stack is full, we can create a dynamic array. So let's consider this as a stack memory, and this is an heap memory, and this is a data. It will point to a array of size 3. And then during dynamic array implementation, in the heap memory, temporary variable is created. Temp variable is created, and it will locate to its direct to its location. So it is of size into 2, so it will be 6 in this case. So it will copy all these elements. So we are iterating all the elements. Here the element, let's say if the element is n, and this is of size 2n. We are first iterating all the elements and then copying these elements to temporary variable. So again, elements will be added for n locations. And then if there are any push operations occur, it will again take place from inside this array. And this temporary variable will be directed back to original, will pointed back to data.
Complexity is time complexity is O of 2n, O of n. You can say O of n. Like we are iterating for n elements. Since we're copying, iterating, we are doing of n iterations and then copying n elements. I hope you got it. And so it's a time complexity for arrays.
For insertion and deletion. So if we pop an item when it is empty, we can say it is as an stack underflow. Same as for a Stack Overflow, we use dynamic creation. So dynamic array is created when the stack is full or when the array is full. So for push operation, it will take O of n. And for the pop operation, it will take O of n, since we are resizing the whole array to a new length. But it is an infrequent shift, but so the average operation we can consider as a O of 1, whether it is a dynamic array or fixed array implementation. So let's move forward and then see the second way of implementation, that is using an array, using an linked list. Okay, let's consider this example. And let's say it is as a stack. So in the array, the topmost element will be element with the last element here, right? So in the linked list, it will store the items in the stack inside a linked list. The top of the stack is the head node, and the bottom of the stack is the end of the list. So let's say this is the top of the node. So it will always be the head. And this is the end of the list. It will be pointed to null. So normally in linked list, what is a common point for every linked list application? So there will be a linked list that has one header and a data and a pointer that will be pointing the next element, next node. So basically, this is a stack memory and this is a heap memory. A header is created in the header object variable is created, and it will point to a first node. So it is a first node of the stack. first node of the linked list. So first node of linked list will always be the topmost, since stack follows last in first out principle. So last element that got inserted is the first one to be removed, and header will always be on the first element. It means will always be on the top element. Okay, so let us move forward. So we can push by adding to the front of the list, and then we can pop by removing the front of the list. Okay. Okay, so let's see how pushing an element, like how inserting an element into the stack, that can be implemented using a linked list. Let's consider this as a linked list. So we have data of 300, 200, and then 100. Let me erase this point. So here the topmost element will be the head 100. So it will be the head, right? Let us also remove this. So this is an 100, and head is pointing to 100, and 100 is pointing to 200. That's how the linked list works. So when we're pushing a new element, like we're inserting a new element into a linked list, what will be happening? So at any case, in the linked list, head will always be the first node. So to insert this node on top of the stack, we have to point the new header as the new node. So this should be our new node, new head. So what we can do is we can create a temporary node that is pointing to a old head. Okay. And the new node, this will be a new node 400. How we can say, and then we can point the new header to a header. So new node will be the header. So header will be a new node. Temporary will be the old header. So it will be old head. So it will be 100 will be the temporary node, and the new node 400 will be the head node. And then this new node dot next. So new node pointer will be 100. So 400 new node is 400. 400 dot next will be 100. So that's how this 400 get inserted on top of the stack 400, and the new header will be this 400 will be the new header. Okay, let me arrange this node then. So 400 is got added. 100. 400 will be the head. Let's say if we want to pop the element from the stack. So let us, this is the topmost element of the stack. Since the header lies on topmost, we can say that 400 is the topmost element of the stack. So if you want to remove 400, like if you want to pop element from the stack, we need to remove the first element of linked list. So how can we delete this this element from the linked list, this node from the linked list? We can just delete the data from this node, from the head node, and we point the header to the next node. So we can just remove the 400 from the stack. How can we remove the data from the stack? using linked list, we can just remove the data 400 and point the header to new header to 100, and again point header to 100. So in the push operation, we're creating a temporary variable, and then we are pointing the new variable dot next, new node dot next into a old header. While the pop operation, we are just removing the data of the first node, and then we are pointing to a correct header. So that's how push and pop operation works in a linked list. Let's go to slides. So this is the algorithm for popping an element from the stack. So we just remove the first node and we point the header to a correct node. I mean to the next node. So for push operation, we insert, or we have to insert the topmost new node to the topmost element on top of the topmost element. So we just create a temporary variable and then point a header to a new element, new node. So this is the example I've shown you. Okay. Let's say if there is no header, it is an heap memory. Let's say if there is no data in the linked list and header is pointing to null. So what happens? What does this mean? If header is pointing to null, so if the head is pointing to null, it means the linked list is empty. Right? If the linked list is empty, that means there is no element present in the linked list. So we can just print an error, or else what we can do? We can consider a variable called node or some variable we can denote x as a topmost element, a top element, and then we can iterate x. So x dot next and then x dot next. So it will be iterating throughout the linked list. That's how we can display the elements in the linked list. And then I will be showing you the implementation of that. So we created a class stack that contains data and the pointer to a next node. And we also created a header of type stack. How can we say if the linked list is empty or not? If the head is null, you can say doesn't contain any elements. So we can just return true, or else we can return false. How can we push the element into a linked list? As I told, we just need to find if it is empty or not. If it is not empty, we can create a new node called new node of type stack that contains the data, and the new node is pointed to the head, and head is pointed to temporary node. So the new node dot next will be the temporary node. As I told, this is the header. So while pushing, what we say, the header will be pointed to the new node. This head will be pointed to your new node, and then this new node dot next will be the old header. So it's just simple one. This is a head pointer that's pointed to first element. So it will be pointed to the new node we are inserting. And the temporary, let's say this is a temporary node that's point to a head node. So new node now become the head node, and the new node dot next will be the temporary node, right? This will be a temporary node. Head is nothing but the first element. So this will be a temporary node. That's how we implement a push operation using a linked list in Java. This is a Java implementation. And same like for pop operation, if the head is null, it means the stack is empty. It means that there is no element in the linked list. So we can just return some integer value. So here I am returning the minimum value of integer. If the linked list is not full, I mean, if it is not null, how can we do pop here? So we have here pop the first element. So this is the topmost element. We can just remove the data from this and then point the header to the correct node, right? So the pop will be the topmost element. So topmost element will be where is the element where the head is located. So head dot data will be the data in the head node. So head will be removed, and then the head is pointed to a correct head. So that means the head is pointed to a next node, and then we are returning the popped element. So for the peak operation, it will just remove the topmost element. So we are checking if the head is null. If it is null, we are printing just stack is empty, and then returning the minimum value of an integer. If it is not empty, how can we get the topmost element from the stack? So topmost element of stack is nothing but where the head part is here present. So we can just print head dot data, the data present in the head node. So that's how this operation works and implemented using linked list. So push, pop, peak, and then push and pop will internally use the is empty and is full operations. And then we also have seen how elements can be printed using how elements can be printed in array and linked list, like displaying element using arrays and linked list in stack. So let's consider complex analysis for insertion deletion in linked list. So at any point of time, we are just pointing the head node to the correct node, right? During a push operation like insertion, during a pop deletion operation, we're just pointing the head node. We're just pointing the head node to a new head, to a correct head nodes. So that's how, so it will take constant amount of time. Like for, let's say if you're pushing 100 element on top of this, on pushing 400 on top of this stack, it will just check if it is empty or not. If it is empty, it will just create a new node and it will point that new node as a head. So it will take constant operation. So we can say constant operation as O of 1. So to delete, so to pop element from the stack using linked list, we just delete the data. So it's a single operation plus, and what we can do is we can point head to a next value. So head is equal to head dot value. So that is one more operation. And then we are returning. So it will be one more operation. So for pop, we are doing 3 operations. It means a constant time, it will taking a constant time. So at any time, for inserting an element or deleting an element from the linked list, it will take constant time complexity. So it can be denoted as O of 4. So for so to access any element in the stack, let's say is a stack of n elements. Let's say if you want to access this element, we need to pop this one, this one, this one. So this will be the our required element. So the number of iterations in the minimum case will be n. So it is O of n. N is the number of elements present in the stack. So for insertion deletion, it will take the same constant time of complexity. It is O of 1. So for space-time complexity, stack memory and heap memory, it is pointing to an array or pointing to a node. We're just adding an element in the stack or removing an element from the array. The same way, we're just adding a new node or deleting a new node and then updating the head node. So it is not taking any extra memory other than this space, other than this array space. So it is not taking any extra space. So we can say the space-time complexity for this is O of 1. So just the auxiliary space that an array is using. It is not taking any extra space. Do you think how we can use the stack implementation, like any real-time applications? So basically, the stack is very useful for data where the elements should be accessed in a reversed manner, right? This is since it follows LOFO principle, the first element will be the last element we inserted, so it will be in the reverse format, reverse order, or undo redo operation, or web browser, right? Web browser, we have a forward and backward option here, so it will all the back operations is inserted. So if you want to go to a back web, so we can, it will be popped, the current window will be popped from the stack, and the old window that we used will be pushed into the stack. So that's how it is implemented in web browser. And the most importantly, stack is used for recursion or function calls. And then we'll be learning about depth first search for graphs. So we'll be see its implementation, how DFS use stacks for searching elements inside a graph. So graph is nothing but a acyclic connected acyclic. So graph is cyclic tree, it will be a tree. So inside the trees, how we're doing a DFS. So this is the stack, and these are the function calls, and this is the call where the base condition is achieved. So all the results from this will be stored, and this will be the final result. The result from this, the upper stack will be stored here, and this one will be stored here. This will be here. So at every time, once we achieve the base condition, this result will be popped out and stored. This will be popped out and stored. This will be popped out and stored, and at the last stack, we'll be getting the result. So that's the main use case for stacks. That's in function calls or recursion. And these are just using array implementation, how memory is used, and based on insertion deletion takes place, memory usage. So we know array is a fixed size. So when memory is an issue, we won't be using array. So for dynamic memory allocation, we use a linked list. And for size limit, we can use dynamic array implementation, or we can give a maximum size before implementation. So in the heap space, the memory space for linked list will be very minimal. So based on memory, it will limit. And for insertion, deletion, we know also our linked list is more faster because the header point will only be only be pointed to a correct node, and then it will be deleted. The data to be deleted is just by pointing the node to a correct node and then deleting the topmost element. So it's just implementing is much easy for these things internally. So access time will be O of 1 for accessing any elements. So in the linked list, like we just traversing the whole list because we need to find the head part and then just go to iterate over the linked list. So this is how the various aspects of arrays and linked list implementation. If you have any doubts, let me know. Thank you.